morning as well as at the 4 o'clock lecture as well, we'll focus on the application areas. Okay, so the application that I'll be talking about is in the energy and in water area. Okay, and for particularly in this, I will now talk about the energy before lunch, and after lunch we will talk about water. And when I start water lecture, I will also bring in some of the biological aspects, because in the water lecture is actually trying to detect E. coli, which is a cell. So I will provide you some background about what cell is and how we can understand it much better. So the first application that I will talk about is related to coal, and I thought since in India coal is something still one of the energy carrier or the currency, so to speak, and you have a large amount of coal power plant is one of the, I will say in India this is the primary energy mix, and then there are hydel, nuclear and so forth, but the coal is still the predominant energy mix. But the challenge across the world, and you may have heard recently in the Paris conference and so forth, there is a huge push in terms of reducing the greenhouse gas emission. So you are not maybe another few years, maybe stronger legislations, like for example a lot of G6 countries and so forth has legislation you cannot burn coal. So similarly, maybe eventually in India as well, this legislation may come forward where you will not be allowed to burn coal. However, you have a reserve of coal, so the idea is whether there is a way using advances in these kind of micro nano scale and understanding of the flow and so forth, whether we can convert coal into some other value added products with still deriving the energy and reducing the carbon footprint overall. So if you look at, I call this as a king coal, because coal still dominates the energy landscape, as I mentioned. In terms of various sources are there, and out of that, typically in India it is not a high grade coal. So so there will be a lot of ash content, and so that also creates a lot of pollution and so forth. So these are some of the numbers which shows that amount of GHG, greenhouse gas emission, which people are worried in terms of burning the coal. So the question was posed is that, is there an alternate route without burning coal? Like when you burn coal in a combustion, coal is a big chain molecule, carbon molecule, there are nitrogen, hydrogen is a big sulfur, all these is a big chain molecule. Is essentially is what you can think coal is a polymer in some sense, is a thick meshy polymer. So if you burn that, you will get CO2 directly and so forth. So is there a way to convert the coal into methane? Because if you convert that into methane, then what happens is there is a significant reduction of GHG. So for example, people show the calculation that if I replace a 150 megawatt coal power plant with methane, then so instead of burning coal, so we convert that into methane, and then we burn, use that as a fuel, then it will be 1 metric ton per year of reduction of GHG. So that's a significant. Okay, and if you look at the scaling, so typically in India thermal power plants are in the 500 to 600 megawatts. So these are typically run by a corporation called National Thermal Power Corporation, NTPC. So typically they are 500 to 600 megawatt units. So if there is an opportunity to replace some of them using in terms of methane, then it would have been a significant cost reduction. So as I mentioned, the coal is like a big polymer. Okay, so it is it has monomers and a lot of fatty acid, alcohols, and there are various processes. So there are biochemical processes, so which particularly microbes. So these are microbes which are present in situ in the coal seams. So if any of you visited any coal seams in India? None. Haven't you been to Dhanbad and things like that? So if you have been, so you'll see that there are various kind of coal seams. So there's something called open cast coal, and then there will be something where you have to dig through it, and then you will see that there's a lot of water in these coal areas. So that in these waters is where actually natural microbes are present. Okay, so these microbes are what are referred to as the methanogens. So there are various types of methanogens which takes place or are present in the coal and can go through various form of bioconversion pathways, and all of them essentially provides the methane. At the same time, you will get there is a particular methanogenesis or methanogens which are acetoclastic bacteria, which actually will convert eventually to CO2 and methane as well. So you will get at the end also CO2, but of course the amount of CO2 is much reduced compared it was a direct combustion. So this is a complex biodegradation pathway, and so again the way we looked at this problem is the similar way in the flow in porous media. So typically microbiologists, what they do is they take the coal samples and put them in a bottle. So these are called media. So in the bottle, what happens, there is a head space in the media, and so they are typically will have nitrogen as inert media, and then they will put the methanogens and allow it to culture. So the methanogens will then convert the coal into methane, and then from the head space you take the methane or any other gas out, put it into a GC, and then look at what are the kind of gas composition happens. So this is typically bottle experiment which is static. In a coal field, things are not static, because this is below the earth surface things, you have flow of water, flow of other microbes and so forth. So what we did is we took the idea of what I showed you earlier in terms of core flooding, which you do typically for porous media. We can pack these coals in terms of a within a core holder or in a porous packed bed, and then actually feed near these methanogens or microbes. So in order to survive microbes, any idea what they need basically? So they need carbon source, or nutrient. So you have to feed some nutrient to it, so that they can thrive in that packed porous media. So we provided some nutrients. So in this case, the carbon source is tryptone. So that's a readily available carbon source that you can use, and then we look at what is happening at the exit, and then eventually we can line this up into again a field scale, which is a big scale simulations and so forth. So from bottle experiment to core flooding to large scale, all these can be integrated in one single place. So typically this shows why we need core flooding, because bottle experiments typically done by microbiologists are not the real situation because of various challenges in terms of the coal mass, pressure and so forth. Everything is under overburden pressure below the earth's surface. So those things are difficult to manage in a coal reservoir. Yes. Yeah.
So basically what we're doing is, in present we mine coal, we process it and then we burn. Right. Now what we're doing here is we're introducing a number of steps in between the whole process. So does introducing this make the whole process profitable?
So I will come up about the profit later on, but the question is not really introducing steps. So these are in situ process. So we are not, so in order to simulate an in situ process where methanogens are there naturally, so these are natural microbes, so these are not engineered microbes that you're introducing into the system. But in order to stimulate that in a laboratory system, what we did is we inoculated this into using this culture media where it has these methanogens. The source of that methanogens are actually is taken from these coal seams. So we have taken the inoculate from the coal seam, and then we cultured that and then introduced that. Okay, but in a natural system, you don't need to do anything. It is actually within the earth's, below the earth's surface. when you are doing the mining, instead of taking it out and burning, you allow methanogens to react with the coal seam. Okay? And what you need to do is to provide some nutrients. So that you can do by putting some wells, like the way we did for oil recovery. You can inject nutrients to the well, and then you can pump out the CO2 which you and other products. And I will show you why it is important, value added, compared not only for the greenhouse emission but other aspects as well. So these are some the mimic reservoir condition, as I mentioned. Anything and the one other important part is using coals, this kind of core holder, you can maintain anaerobic conditions. So these methanogens below the earth's surface, they only thrive in anaerobic condition, means that they will malfunction if there is a presence of oxygen. Okay, these methanogens. So that's the characteristics of this methanogen. So when you are dealing with this kind of system, you have to purge everything by nitrogen. So the entire system is inert. So that, and also when you are putting inoculum, the medium has water. So you have to water, always have dissolved gases, and typically oxygen will one of the dissolved gases. So you have to take oxygen out from the inoculum medium. So these are can be a tedious process as well. So what we did is this is is a very complex is really a mechanical engineering system or a chemical engineering process system. You can imagine this is a process diagram we developed, which has a lot. This because it has to run for 50-60 days, so it cannot be done manually. So it has to be completely automated with some sort of a GUI running, so that it helps to collect data and so forth in a very automatic. So essentially you have an upstream where you have a syringe pump which is injecting the microbes, the nutrients and so forth, and the downstream you have the so-called holders which will help to collect the effluent, and then you can pass that effluent into further analysis. Okay. So this is what a system will look like. Typically I ask my student always have this experiments in a trolley kind of setup, which looks very neat, and also you can move things as and when needed. So this is what the upstream side is. These are the syringe pump, which typically from Teledyne, and then the downstream as well, where you have the piston accumulator, where you actually keep, because everything needs to be pressurized. That's the real challenge, because if it is it's not, if any part of this is depressurized, means outside air will come in, so no longer it will be anaerobic condition. So keeping the anaerobic condition, everything has to be completely pressurized. It is so this kind of GUI we have made, and I believe you guys are much better in software development. So this is using a LabVIEW and CVI. We're actually programming in the national CVI, and then you can make all these things. You can make emergency stop if there is a malfunction. And we did is we also had a camera, which, for example, in night and stuff, if there was a spill and so on, we can actually from IP address from home, we can actually shut this down as well, the entire process. So we measure a lot of transport properties like permeability, porosity, and so forth, which are important to characterize the porous media. As you can imagine, it went for 90 days. Then you can look at the amount of, so you can collect a lot of data out of it. So for example, the porosity, we can look at what is the porosity using water injection. As I mentioned, there could be two different ways of measuring porosity. One is through material balance, and then water by using saturation as well. So when you calculate the permeability, so this is often one measures the permeability, and then you can do some correlation. So there is a famous correlation called Kozeny-Kármán correlation. So this correlation provides the permeability, and that permeability in those Kozeny-Kármán correlation these assume that the particles are the spherical particles, the way we have seen for the glass beads experiments before. So one can correlate those things as well. So you can imagine that also over time, this is very interesting, which you will not see in most of the porous media, is over the time there is a permeability variation. And when I look at actually the SEM, so now I can take the coal after at various time interval we have opportunity to unpack and take this coal sample. Say for example at the very end, after 90 days, there is a biofilm formation. So that attachment of the microbes. So you can see that there is a microbe and they're attached into this coal structure. So you can see that there is a proper formation of the colony, so to speak, of the microbe has taken place. That's very critical to maintain those kind of proper formation of the colonies. We can look at what are the molar ratios of methane and CO2 and so forth, so that as I mentioned, there are pathways not only produce methane but also CO2. So we can use so these are soluble, right? So you have to do some solubility correction. So how one does solubility correction? In chemical engineering you should be knowing, by using Henry's law, right? So you can use Henry's law to correct for the solubility, because as I mentioned, these will be within the effluent, right? So these CO2 or methane will be present within the effluent. So you have to make some solubility correction so that you can actually get the actual quantity of carbon dioxide and methane. So you can see that with solubility correction and without solubility corrections, these values, these are experimental values that are shown. So in terms of your question about what else in terms of economics and whether it makes sense economically, so you can see the advantage of this is you are getting a very other value added products like acetic acid and succinic acid. Particularly if you are in chemical engineering, you may be aware succinic acid is used for pharmaceutical industry in a very big way and is a very expensive as well. However, through this bioconversion pathway, you can get succinic acid at a very good rate. So these are the value added product you can get out of this process. So what we did is something called a heat map, and microbiologists use this kind of heat map to take at the various point of our our process. So these are initial phase. So these are all the at the very end we are taking the effluent. So we are collecting the effluent at the various 0, 1, 2. So these are all the effluent stages, and then we did a heat map to look at what are the key effluents that are coming out of these processes. And so you can see that there are various kind of chemical compounds that can be produced by this process, and the color indicates the relative concentration. So typically if you are in microbiology, we often use these kind of heat maps. So this is what we have drawn, a heat map to understand what is the metabolite kind of map in this process, so which gives us also a better understanding of the system. So as I mentioned, also it's critical to understand what is happening inside the system. So we did a lot of SEM, which is very tricky, because you can imagine you have microorganism on a substrate, okay, and you are doing the SEM of that. So it is not just a normal material we are doing, but it is a biomaterial that we are doing a scanning electron microscopy. So we did this, and we can see that these are actually these rod-shaped bacteria that are present in the system based on, say, in this day 90 and so forth. Then you can put some overburden pressure as well. So you can look at the impact of pressure in the system. So in this case we maintained pressure through an oil system so that it maintained a constant pressure into the core, and we designed these core holders, and then this is what now is the biggest size when you maintain the pressurized system, and this, and you can see we have to always make sure there is health and safety is paramount in our work. So then no visitors shouldn't actually jump inside the experimental setup. Sometimes the people get so excited they want to touch it. So we want to make sure that people are not getting inside. And when we did with this new system, what we also has number of pressure and temperature tabs basically. So one other thing that we were interested is what is the natural temperature, how much temperature, because microbes needs so these methanogens will be thriving at a particular temperature. We want to register what is the temperature change in the system and what is those optimal conditions. So I think these study kind of gave us a way to understand that beyond the typical combustion, we can as an energy source we can use some of the advances of microscopy as well as flow in porous media to tackle these kind of challenges. Okay, and of course this in this work I have the entire team which has people from geophysics, because we have to understand how the geological formation of coal are. So there are people for hydrologists. So these are people who look at the water chemistry. So there are carbon isotopes in the water seams that will actually tell what kind of pathway these microbes were taking. And of course the microbiologists were very essential in terms of in letting us know in terms of S16 RNA. We did all the profiling and to pick those metabolites or those methanogens that will make sense for a rapid production of methane. Any question on this? Yeah. Yeah.
So in normal burning of coal versus this process, what is the waste volume ratio?
Waste volume.
Exactly. When we burn coal, we have a particular waste product that is ash, right?
There is a main CO2 is produced.
CO2 and ash.
Yeah.
And
here there is no burning is happening, right?
No, sir. So, but when we provide the inoculation process, there are some waste products.
Not waste. So this is new. Whatever the byproducts are coming in. So the byproducts are all these are the byproducts. So this is the byproduct of the process of the methanogens. So
all of them can be used.
Not everything, but you can use most of it basically. So that's the advantage of it. This is the byproduct, and of course what happens is, as I mentioned, carbon is a big molecule, right? So it is getting fragmented, and so there is a depolymerization process that is taking place because of these methanogens. So if you look at the coal structure itself, it has the carbon, hydrogen, nitrogen, sulfur, these bonds. So these bonds gets broken due to this process. So this is what depolymerization process takes place, and then it goes into the methane, CO2 and so forth. So and other products. So that's what these other bioconversion products are. Okay. So there is no ash formation because there is no burning process. Everything is in situ. Okay. Any questions? Okay. So next, let's look at another part of this energy, which is in terms of the fuel cell. Okay. So fuel cell is an energy conversion device which directly converts hydrogen and oxygen into electrical energy. How many of you are aware of fuel cell? Is anyone? Fuel cell? So not much, so I may provide you some more background on this. So typically, these are the fuel cell car, which are, you can have a car and now even people have battery operated car. For example, Tesla is one of the pioneer. Elon Musk, who has come up with this battery operated. So these are lithium ion battery operated, but fuel cell is there's a big difference between fuel cell and battery. Okay, the fuel cell is an energy conversion device, whereas battery is an energy storage device. So that's a big difference in terms of battery and a fuel cell. Let's look at what is a fuel cell will look like. So a fuel cell in its heart will have something like a, yeah. I think your voice is a bit loud, even if it's bothering me. If you have something contribute, you should contribute and let us know if you want to contribute. So you have the electrolyte, and then there is this anode. So these are electrode, and then there are flow paths, which is often referred to as a bipolar plates, which provides the flow conduit. So in a fuel cell, this is pretty much the structure. So you have an anode, cathode, and an electrolyte sandwiched in between, and then you bring, say for example, in a hydrogen fuel cell or a PEM fuel cell, you bring hydrogen, which is the fuel. So it will go in. So hydrogen will go inside through the anode. Okay. Then it will create proton. Okay. So while creating proton, then it will leave electron out. So these electron will move through the outer circuit. So this is where you can generate, put a bulb or something, generate electricity. Then this electron will come in contact with air, or in other words, oxygen. It will come, the oxygen will come in, they will react and produce water. An excess oxygen, and so is the products out. So this is where reactant out, or the fuel out, and this is the product out. Okay. So this is what a fuel cell will look like. So hydrogen and oxygen, forming water. Okay. So the water is produced, which is always a challenge, because these if I look at this part of the cell, if I zoom into this, what I will see is it is made up of a lot of fibers. So these are fibrous material. So which is referred to as the gas diffusion layer. So essentially gas diffusion layer is a porous media. Okay. So when you are operating this cell, the fuel cell, you don't want water to block the pores. Okay. So what one can use if one has to stop the this porous media is somewhere maybe pore size are in the order of maybe say 100 micron, the pore size are. Okay. So this is what is both the cathode and the anode. These are porous media, which is referred to as a gas diffusion layer. So typically is the commercial name of this product is referred to as a Toray paper, okay, or a carbon cloth. But as I mentioned, this water is produced because water can be detrimental to the fuel cell because it can flood everything, right? If the water is produced. So then if there is a flooding, then the reaction may stop. Okay? So how one can prevent this water moving back? What is the way you think we can arrest water?
Keep the whole setup pressurized so that the water cannot move.
Well, water will go through some gradient, right? So there could be some diffusion of water in the system.
We could use this water itself to use this water itself to produce oxygen.
No, water to produce, that's a very difficult job. That splitting of water produces the energy intensive process rather. So you have to work with the pore size. So way we arrest the water is what we do is we actually put another layer in here, okay, which is referred to as MPL, which is the microporous layer. Here the pore size is in the nanometer regime, okay, and that allows us to avoid any kind of backflow of the water. So that's another challenge. So one important thing. Why in this case hydrogen will produce proton? What is if I put hydrogen in any porous medium, it will produce a proton? Or what is the reason? Why such reaction is taking place? Anything bombarded at high speed can create a proton? Is it possible? Think about it. This is your high school chemistry. What it needs, what is the requirement for a reaction to sustain? Catalyst, right? So I have to put some catalyst in here. So I put some catalyst. So this is a catalyst. Typically it will be platinum catalyst, so that's why it becomes expensive, but the loading will be very small amount of platinum that I can put in here. If I have to zoom into this area, what I will see is that you will have the catalyst layers, and then you will have this. They need to be bind. So some binding material will be ionomer will be there. So typically an ionomer is PTFE, Teflon. So you will see some Teflon binded in this process. So it's a very complex system because it has the ionomer, it has the platinum catalyst, as well as the carbon paper, the gas diffusion layer itself. So it is a 3 solid phase problem. It's a 3-phase problem. The 3 phases here are the ionomer, the platinum catalyst, and the carbon black. Okay, carbon black coming from the GDL. So this is everything all together is present, and the ability of the electrochemistry will be highly dependent upon how much ionomer that I put inside this catalyst layer. Okay, so something is happening in here in terms of the chemical reactions. Okay, so the chemical reactions will be, so there is electrochemistry involved. Okay. What else is involved in this basically? So reaction is there, what else? So there are flows, right? So there is flow in the system. There is what? What is happening in here? The ion transport is there, right? And then overall, there is a charge transfer because electron transfer is also taking place. So this is one of the most fantastic, micro nanoscale transport system that you can ever see. It has everything inbuilt in it. It has, and most of the system we study, they don't have the electrochemistry in it, but it has the electrochemistry because all the chemical reactions are taking place. So if I have to look at, let me see where I can write maybe in here. So if I have to write conservation equations for this kind of system, what kind of conservation equations will be? Or governing equations? So there is a mass conservation, right? So that's the fundamental of our equation. So we can write some mass conservation equations. So mass of hydrogen plus mass of oxygen coming in, mass of water that is produced plus mass of the reactants, right? The reactants that are coming out, which is unspent, which is the the mass of the products, which is the MP plus, which is reactant unused, so which is out, say product out, reactant out, which is the unused fuel as well as the unused part of the air. Okay. So this is one conservation we can write, correct? What about energy conservation? How we can write energy conservation here? So you have to have, when you're writing energy equation, you have to have a control volume, right? So a control volume should be around this, right? So when I have a control volume around this, right? So anything which is happening inside shouldn't come into your picture, right? So how one writes energy equation, are you aware? So any conservation equation is written in this form, right? Change of things within the control volume. So in this case is energy is equal to energy that is coming in minus energy that is leaving the system, right? So this is any conservation principle, same as mass, except within the control volume the mass is a mass, there is no change of mass within the control volume, so this terms get 0. Mass in is equal to mass out. Energy change of energy within the control volume for a steady state process, if the system has achieved steady state, so then it becomes equal to 0. So then it becomes energy in is equal to energy out, correct? So what is the energy that is coming in? Hydrogen. How we can quantify that energy? With the enthalpy, right? So the mass of hydrogen times is enthalpy that comes in, mass of oxygen with is enthalpy that comes in. So this is m dot H2 times the enthalpy of hydrogen plus m dot O2 enthalpy of oxygen, that is equal to your enthalpy of water, this product out, its enthalpy plus the reactant enthalpy. Now, how we get these enthalpy values? The cell is operating, say, at a temperature. Typically, they will operate at temperature, say, 80 degrees C or something like that. So, how these enthalpies are calculated? Through enthalpy of formation, right? So, we have to really look at what is the value of delta G or delta H rather in which table that provides these enthalpy values. So, there is something called Genoff table, right? So, we have to look at the Genoff tables. So, there is a standard heat of reaction are given, or heat of formation reactions for hydrogen, oxygen, water. These are given at STP. You have to make a correction for the change of temperature. It means everything is given at 25 degrees C. So, that enthalpy of formation is 0. Okay? So, anything beyond that, you have to add that delta H value and then come up with this. Okay? What about the second law? How we can write second law? So, what is the second law for this process? Not sure about second law. So, always remember conservation way of writing. So, same, I can write second law as the change of entropy within the control volume. So, which is the ds dt within the control volume. This is equal to entropy that comes in, which is m times s in, because there is a mass flow rate. Entropy that leaves the control volume, m times s out. What else is there? So, that is the only difference in with respect to energy versus entropy. So, there is entropy production term, okay, which is greater than equal to 0. Equal is for a reversible case. Always there is now, there is second law. Don't get scared about second law. It is just again you can always recast this in terms of conservation equations, right? So, same thing, entropy. So, change of entropy within this control volume is due to entropy that comes in, entropy that leaves, except the same thing in terms of energy, but now energy cannot be produced and destroyed. So, there is no energy production term. If you are able to do energy production, then everything would have been solved, our energy crisis. But for entropy, there is an entropy production term, okay, and that for a reversible process is equal to 0. For irreversibility, for real process greater than 0. Again, this for a steady state problem, this is equal to 0 for steady state. If this fuel cell has reached the steady state at a temperature of 80 degrees C, then we can plug in these values of S in, S out, and then we can find what is the entropy produced for the system as well. Also, there is the ion transport. So, ion transport, the governing equation, what will be the, if I have to understand the ion transport, what could be the governing equation for ion transport? So, how we do ion, this you have learned in your ion transport in electrokinetics, you have learned this, something called Nernst-Planck equation. So, we will use Nernst-Planck equation to so it will have the coupled of the flux, ionic flux, or the and the velocities, right. So, the velocities and the ionic flux will be coupled in this. So, this is ion flux and this is the velocity. So, they are coupled in a Nernst-Planck equation. Okay. Then you have the electrochemistry. Electrochemistry will provide us with the current density, I, or current density, which is provided through something called a Butter-Volmer equation. So the electrochemistry is defined through a Butter-Volmer equation, where the Butter-Volmer will dictate, because you have the platinum catalyst, how much coverage of that catalyst, what is the type of kinetics that you are using. So based on that, you can find out the current density, and that is again can be used in Nernst-Planck equation. So you can see U is again present in here, right, for the mass flow rate and so forth. So it is a highly complex problem. It's a very coupled problem that you need to solve. This is non-trivial, and you have to worry about various boundary conditions as well, because what is the, so you have to assume some concentrations, ionic concentration, as well as the flux concentration. So what is the concentration of oxygen, hydrogen at those layers? You have to have a fairly good idea about these things. Okay. So it is a very complex, even though it looks benign, this fuel cell itself, the modeling of fuel cell is a very complex, and it has various scales as well. So these are, in terms of micron to millimeter, again micron, these are flow paths which are in millimeter. So also there are various scales present in the system. So it becomes a very complex problem to solve. Any questions you have on these? I believe you have done ion transport, right, in your first part of lecture, right? So you are aware of how to deal with the Nernst-Planck equation. So essentially what it does is you look at the ionic, how the mobility of this ion is taking place in the system. So this electrolyte is a particular electrolyte, is a proton exchange electrolyte. So it is available commercially through Dow Chemicals. This product is referred to as a Nafion membrane. So Nafion is the membrane, which is a trademark of a Dow Chemical, which you can buy, which will allow proton to move in it. So it has a sulfonic group. So the proton hops through this sulfonic group of that membrane, so that it allows proton to migrate. Okay. So this is what Dow Chemicals sell in the market as a Nafion membrane. Is this clear? Any question on this? So at the end, what you will do is you will start drawing current. So when there is no current, the EMF of the cell, the electromotive voltage of the cell, is at the highest. So moment you start drawing the current, means the cell reaction has taken place. So it has to overcome some activation barriers. So you may recall in your high school physics, there is the reaction coordinate and the product coordinate. So the reactant goes into the product through an activation barrier. So typically they are modeled through some sort of Arrhenius kind of a reaction equation. So it will have some reaction rate, which is exponential nature of minus of the free energy or the activation energy of the system divided by kT. So the first drop that you see is due to that component, which is the activation component of the cell. The second part is due to the resistance. So each of this will have finite resistance into the system, because you are flowing, driving current out of it. So they will have finite resistance. So this is what the final drop you see at the voltage as you are increasing the current is due to the resistance of the various component of the cell. The last part is where, as who are in the area of mass transport are very interested, because that's where the mass transfer losses takes place. In other words, you have drawn the current so much is that flooding has taken place, the catalyst no longer is amenable for any further reaction. So that's what is referred to as a mass transfer limited. In other words, this fuel cell is ceased to exist. If there is no voltage out of the fuel cell, means the fuel cell will not run. So this is the journey of a fuel cell from its starting to the very end, and you want to avoid or want to delay this mass transport or mass transport limitation as much as possible. So in other words, you don't want to have flooding. That's why you put a MPL, microporous layer. You maintain the integrity of the catalyst layer, so using this ionomer and so forth, so that you can start try to push this. And that's where porous media and the transport becomes very critical, because here not only you have a transport within the, say for example, the hydrogen or oxygen is transporting not only in the water molecules that we are talking about, but there is a transport across the various scale of the porous media, as I have drawn earlier, because you have a GDL, which is a larger pore, micron, and the MPL, which is a smaller pore, which is a nanometer scale. So the transport of porous media across this becomes very critical. And what else? What other complexity you see in this? This is fundamentally one big challenge in this fuel cell as well. So typically you will not be using oxygen, right? So air is the one which you plug in. So air is a multi-component system. It has oxygen, nitrogen, water vapor, and so forth. So what you are seeing is the biggest challenge in this case is a multi-component diffusion. Okay. So that means this is a non-Fickian process. So Fick's law no longer is valid in this system because it's a non-Fickian process. Fickian is only diffusion is for binary system. It was if there was only hydrogen and oxygen diffusing, it would have been Fickian. You have the iron here, you have the water, so it's a completely multi-component diffusion system. So it's a non-Fickian process, and that's what it becomes more challenging as well. So we try to take care of some of the understanding of the diffusion and overall the transport mechanism of the fuel cell. So what we did is we created we take the porous media, so essentially this either the anode or the cathode, any one of this porous media, we put it into this into a diffusion bridge. So essentially there are parallel channels, and you put a porous media into it, and then you allow hydrogen or oxygen to diffuse within the porous media, because what you are trying to address is what is the effective diffusivity of these materials, because these materials are not, if you look at scanning electron microscopy of any of this gas diffusion layer, these are fibrous materials and they are intertwined. They have a in plane permeability as well as out plane permeability. So they have permeability in the Kx and Ky directions. A very complex porous media. And top of that you have the MPL, the microporous layer. So you have to understand what is the effective diffusivity for these kind of systems. In terms of permeability, also is a challenge, because then you have to measure the permeability. As I mentioned, permeability can be measured through a pressure drop. So what we did is we blocked the either end of the channel to allow the fluid, in this case, say for example oxygen. We are looking at permeability throughout this porous media with respect to the oxygen. We measure through the flow meters the flow rate, and then we calculate what is the permeability of the system. Also we calculate the mass transport, so in other words mass flow rate as well of nitrogen and oxygen. So now you have a dual system, so nitrogen as well as oxygen diffusing out of each other, and then we measure this across the end of the at the exit as well. This is typically an experimental setup, is all is in a panel, everything, and then you have a data acquisition system to run this. So these mass flow controllers are very critical, because it has to, the precision of the mass flow controls are extremely critical for this system. So what is the experimental data that you look at? So what you look at is the mean velocity versus the pressure drop. So that is one data that you will be interested. Other is the mass flux or the oxygen flux versus the pressure drop. Then what you do is you apply some transport model. So that's where the challenge, as I mentioned, of fuel cell is. Alone experiment, just doing experiment will not give you the results because of this complexity of these diffusion processes, where there is a molecular diffusion, there is a Knudsen diffusion, because in the microporous layer the pores are in the nanometer, so there is a Knudsen diffusion taking place, and there is a bulk flow, because here you have a hydrogen and oxygen sent through a given mass flow rate. Okay, so there is a bulk flow, so there is a convection taking place. All these mechanisms are coupled in this case. So you have to use some model in top of these experimental data to come up with this bulk like permeability. Then you have the Knudsen diffusion, which is the decay, and the effective diffusivity as well. So these are the key things one needs to do in terms of extracting the data. Yeah.
So since the process which is occurring here is typically higher than the room temperature at about 80 degrees C, what are the effects of temperature on the porous media flow in these cases?
So the temperature impact will be of only two natures. So one, it can go up to 100 degrees C as well. So if it is going slightly around 100 degrees C, so you will have the impact is in the water. So it will be no longer liquid state water, so it will be in the vapor state. So that will have to be taken care. So typically you want to keep this everything in the liquid state. So anywhere between 60 to 70 degrees C you want to keep, so that the water is still in the liquid state. So, and that has an impact in terms of the open circuit voltage. So E, the electromotive force, that when there is no current drawn, the E is purely given by how one can calculate E, EMF of a cell. What is the function of? Is the function of the Gibbs free energy. Okay, so the Gibbs free energy will based on what is the Gibbs free energy corresponding to the water as a molecule, water molecule, liquid water, versus what is water in terms of the vapor. So then the cell voltage at the zero current will vary. So that is the only implication in terms of the temperature you have. Yeah.
From where will we get the hydrogen? From a chemical reaction?
Hydrogen, you have to produce hydrogen. So there are various ways to make hydrogen in the system, and they have to be stored either in a cylinder or in terms of metal halides. So you can have storage in the metal halides, where it can depressurize the system and it can give hydrogen. So this is a challenge. That's why these batteries are now becoming more attractive, because batteries, the lithium-ion battery doesn't need any kind of exotic fuel. So hydrogen, our challenge is our economy hasn't been move into a hydrogen economy. So that's where it is expensive in the first place to produce hydrogen.
Sir, can we do similarly for oxygen? Because if we do so, then the problem of diffusion of all the gases will be eliminated.
Oxygen, what I'm not getting.
I mean, can we do the
same oxygen is here. Hydrogen and oxygen are the reactants.
Yes, sir. I mean to say, instead of drawing in air, can we also generate oxygen by some process? And if we do so, then the problem of non-frequent diffusion will be eliminated.
No, but you have to generate energy, right?
What he means to say, sir, is what if we
generate oxygen also by some chemical process similar to generation of hydrogen?
Yeah.
Can we do?
I'm not.
What if we break water into its elemental components?
Not by breaking water, because if we break water by electrolysis, then again we will consume.
Yes, exactly.
I mean to say, what if we generate oxygen by some chemical process?
Oxygen by chemical process.
So that we can let in pure oxygen instead of air.
No, okay. So you are saying instead of so then you can have oxygen coming in, but still you have the water, diffusion of water and the diffusion of the ions. You're still there, right?
So for that we have already put.
So even if you have hydrogen, oxygen, water system is a 3-component system, right? So still you will have more than 2 component to deal with at a minimum, basically. But typically using oxygen alone is not an economy economical way, because air is much freely available. So just using oxygen may not be economical.
And how do we counter the reducing as well as the oxidation properties of hydrogen and oxygen individually on the material of the battery?
Battery? No, fuel cell.
Fuel cell, sorry. So how do we counter the hydrogen is reducing?
So that's what is happening, right? Electron is giving out. So that's what, and the material.
So what if the hydrogen and the oxygen reduce or oxidize the material compound?
No, these materials, you mean these anode, cathode. So these are inert. These are all carbon-based compounds. So they are nothing. There is no physioabsorption or chemioabsorption of hydrogen taking place. The only place where hydrogen can have some impact in absorption is in this bipolar plate. So what they do is that they coat this bipolar plate such that absorption of in this case hydrogen doesn't take place. Okay? Otherwise, in neither of these cases there could be any issue about hydrogen absorbing the material. Okay, anything else? So this may be something new. So when we talk about Darcy law, the Darcy law is in the first part of the equation. So dP dx, the pressure drop, is related to the permeability, the viscosity, and the velocity. So that is what the Darcy law is. So BV is the Darcy permeability of the system. But what we have is when you have a convection of this nature, there is a high velocity fluid coming in. So you need to have a correction of the Darcy law. So the correction to the Darcy law is given by this V squared term, which is referred to as a Forchheimer equation. So you have a Darcy permeability, and then there is something what B1, what we refer to as inertial permeability. Because of the inertia of the fluid, there is additional permeability in the system. So in a broader sense, there are two different kind of permeability. One is the bulk permeability, which is given by the Darcy equation, and then there is the inertial permeability, which is the B1. The second part of the problem is more complex because here what we have is when we have multiple components, or where there is a Knudsen, where the particles or the gases are not only colliding among each other but with the wall, because the wall of the passages are so small, then what we have to deal with is something called the Stephen Maxwell understanding of gas dynamics, or in terms of diffusion process. So this is what we have done here. We have included something called a binary friction model, essentially looking at the Stephen Maxwell equations. So these are fundamental equations where through the derivations are complex. Essentially what you do is you get a mass flow related to the bulk permeability. So this is the bulk permeability, and then you can get an effective Knudsen diffusion, which is the subscript K referred to as a Knudsen diffusion. So that equation, because you are measuring, if you recall, you are measuring the mass flow rate. So the mass flow controllers that I have shown in the previous figures. So those experiments, you know what is the mass flow rate and the pressure drops. Through that, these two equations are really critical to derive those quantities, the transport quantity. At the end, you will be interested to plug in the transport quantity. In these equations, everywhere you will see the transport quantity, which is the unknown parameter. Okay, the known parameters are all your mass flow rate, how much oxygen, hydrogen. These are all in your control. But the thing that is not in your control is all these transport quantities, the permeability, the effective diffusivity, the Knudsen diffusivity. So these have to be measured for case by case basis. So that's why this equation is beyond a Fickian diffusion equation. Okay. So these are some, as I mentioned, there are various ways to look at it. So these are something referred to as a binary friction model or Dusky gas model. These are quite involved, and I gave you a glimpse of it. So this is where the interspecies forces or Stephen Maxwell relationship has been evoked in terms of the chemical potential, and because each species are interacting as well as bombarding with each other. So you have to look at that species transport. There is a Knudsen friction because of the flow passages are small, and then there is a viscous force, which is also there is a viscous friction parameter which is derived through these kind of expressions as well. So this entire process is very complex. Is not a simple Fickian diffusion that you see, which is will have only a concentration gradient and a diffusion coefficient. Okay, so this is really something which is quite complicated, and that's why the challenge in the fuel cell. So, but hopefully you can appreciate that when you have a multi-component system with Knudsen diffusion, you have to deal with something which is beyond Fickian diffusion. So these are various kind of porous media, or we use various gases. The reason that these gases are chosen are simply because you have a microporous layer. So if I look at it comes from the mean free path with respect to the your characteristics length of the pore size. So if you look at oxygen, is mean free path is somewhere around 69 nanometer, whereas if I use helium, I can get an immense large amount of mean free path, which is 190 nanometer. So that helps to deal some with, for example, in the microporous layer. And then we do diffusivity experiments in terms of oxygen and nitrogen as well. So what we have is so this is how you can imagine this is how a system will look like. You have a gas diffusion layer, gas diffusers, they are sandwiched together, and sometimes you have the MPL, the microporous layer sandwiched together, and these are SEM images. I'm mentioning it has a permeability both in the X and Y direction, and you look at the permeability measurements, and then you come up with the effective permeability or effective Knudsen diffusivity, which will depend upon the so-called the tortuosity of this tau of this porous media as well. So the tortuosity is also we have to take into consideration when looking at these systems. There are some literature value as well available in these kind of material, and then you look at the diffusivity. For example, this is again the mass flux versus the delta P, and then you can come up with the oxygen diffusion coefficient in terms of the GDL in this case. You can look at the MPL as well. There are certain discrepancies between the model. So between once you plug it back, you will see there will be some difference between the model as well as the experimental value, which is quite expected. So why these are critical is because most of the science of this nature of understanding the permeability and so on has been empirical in terms of, for example, the critical parameter is what people have been using is something called Brugmann correlation. So if you look at the Brugmann correlation has been derived for coal particles. So these are spherical particles for which Brugmann correlation to understand the diffusivity of porous media has been derived. But as I have shown in the scanning electron microscopy of graphs of these GDL and MPL, they are nothing close to a spherical particle. So these are fibrous material. So of course Brugmann correlation doesn't apply. So that's the reason you have to have these kind of fundamental understanding of the porous media to derive the actual quantity. So we can see that the diffusivity that we measure is almost 1 times lower than what has been predicted by Brugmann correlations, which has been the used quite heavily in the porous media. So with this, I think these are the two kind of energy applications. There could be, we can talk about a lot of other energy applications, but these are something which I thought has some similarity with some of the things in chemical engineering and other engineering systems you are currently doing. Any questions you have? Something? We will take up the water part in the next lecture, and if there is none, we should meet back at 4 o'clock, okay? And then we will go through the rest of the. You got the lecture note for the water as well, or it is not here, but so I will just put my laptop. Okay, so I'll see you all in 4 o'clock.